Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, everyone.
Good afternoon,
Salam. Good afternoon.
Betul.
Afternoon. Afternoon. Okay. Yeah, I have something that I need to maybe like from I think during the tutorial like especially for tutorial group 1, I remember we sort of like got stuck in one of the question, right? I think in tutorial group 3 I managed to show the whole thing, but for tutorial 1 and 2, just a quick explanation. I said I would like to do a video, but I think I'll just take like 1 or 2 minutes just to explain how can you actually do it. Okay, so for the question, remember this question, Tn over 2 and 2 to the power of n. Okay, so what we do is that we have our a. It's just that we take the form as what we have here, and we said that our k is n and our n is 2, and we compare between log a base b, which is 0, and then we compare it with our k, which is n, and we know that our n value is 1, 2, and so on and so forth because it's an exponential function. So therefore, this is case 3a, and we just apply the formula and we'll get theta of 2 to the power of n. Okay, so this is if we use our method, the one that we try to find value of a, b, k, and p. Okay, and bear in mind, what we are actually doing is that we are trying to compare between this function, okay, which we call as fn, with this with this recursive function that we call gn. So what we're trying to do is that we want to find out whether this function is upper bounding this function, or this function is upper bounding this function. Okay, so basically this is what we're trying to do. Okay, so this is if we're using the one that we look inside our lecture. But for those of you, I think that question would be much more logical if I explain it using the master theorem presented in common, whereby if you look at common, of course there's still 3 cases that you need to check, but the comparison is between so here in this case the value of a, b is the same. Okay, so the a would be the value of a, and this one would be sorry I should not do that. Okay, so maybe I can just write it again. So the a, t, n over b. So this form is still the same. So in common method, okay, what we do is that we compare between n power of log a base b with fn. Okay, which is much more clearer to see the definition that I mentioned just now, which is we're trying to compare which function is upper bounding which one. Okay, whether between the gn as well as the fn. Okay, so in this case, if you look at our question, we know that our fn, the running time complexity for our fn, which is 2 to the power of n, is 2 to the power of n, because it is an exponential function, and our n, so we call this as gn. So our n log this one is 1 base 2, so we're going to get n to the power 0, which is 1. Okay, which is, we can say that this is case number 3. This is case number 3, and therefore the running time complexity for that function would be t of n equals to the running time complexity of fn, which is 2 to the power of n. Okay. All right. So that is just something that from last week. Okay, tutorial question from last week. So that is how you can you do it. Okay. All right. So for this, oh, I forgot to start recording. I'm so sorry. Uh, okay. Please remind me if I don't, if I forgot to start the recording. Okay. So is it recording now? Right. Okay. So today we're going to be looking at another topic, which is sorting algorithm. All right. So we're going to be looking at several sorting algorithm. And the good thing about this sorting algorithm is that it can reach the running time complexity, the performance of this sorting algorithm can reach order of n. Okay, it can move towards the running time complexity of order of n, which is a linear function. Okay, so uh, uh, oh, I think I need to make an announcement regarding next week. Okay, so next week, as you all know, we'll be looking um, at the string matching topic, but we plan to have it like an asynchronous mode, whereby we give you a bunch of videos for you to look at, and then prepare the lab, okay, for your lab viva. Though for my group, I still open like maybe if you prefer to have a synchronous rather than you doing the self-learning, I can still do that. So I will open poll, maybe in Telegram, to see whether you prefer to, uh, how do you call that, self-learn over the weekend and do the lab viva, or you prefer to have a synchronous lecture next week, still like just like a normal lecture. Is but then the time that you need to do the implementation would be a little bit less time, because supposedly you can start by Thursday. I believe that the Tajrina is going to publish the question either tomorrow or Thursday, the question for your lab viva. Okay. And yeah, I leave it up to you. The material is already on Spectrum. That you can have a look at that, or if you prefer to run through the topics with me, please let me know. I'm fine as well. If you prefer to have like a synchronous session discussing that topic. All right. Okay. Speaking of which, I see your you are aware, right? You have to register your members through Google Sheet link that I have posted. Let me try and see. Uh, for those of you who do not have a group yet, please put your name in the no group name. And then I did notice something. For make sure, okay, your group member is within the same tutorial session. Okay, so I noticed that in the list there's one in group there's tutorial 3 in session 2 and 1 and 2. So please, recording has stopped. Oh, thank you. Okay, why is it stopping? Wait, let me try to start. I cannot start it again. Thank you. Start recording again. All right. So if you look at the
Hello,
Google
what's up, guys?
sheet,
Now I
okay,
will
I noticed that for
show
group
you.
5, I have someone with no name. From group T3 is inside T1 and T2. So please make sure that T1 and T2 can combine, but for T3 you cannot combine. Okay. And for group T4, group 4 and group 5, please refer to instruction from Dr. Raja Jamila. So I can see that I'm not sure whether this is all. I need to check how many of you because I think today is the last day for Add and Drop, right? So possibly by tomorrow I should be getting the final number that will be under my group. Okay, so but then for those of you who will be with me in tutorial 1, 2 and 3, please register your member inside here. Give your name if you do not have any group, okay, as soon as possible, because I plan to have like a group discussion during our tutorial this week. So it's better that you have a group so that you can work together to work out the answer for the tutorial session this week. All right. Okay. So that is that. All right. Any question about this class?
The Viva next week will be a group assignment, right?
For my group, I will start my Viva in week 5. So I will post slots. So if like I will post slots throughout the week. So you can choose which slot you and your group would like to do the lab Viva. Okay.
Okay.
Yeah, so like for me, I will give you extra time. Like even though that the question will be posted this week, but I think since you will need some time to get familiar with Python, that's why I think instead of week 4, I will do my Viva in week 5. Okay, so look out for the slot announcement where the group leader or the group representative can register which slot that you and your group would like to do the Viva. Okay.
Okay.
All right. So any more question? Class, you good? Okay. All right. So let's continue with
Doctor,
our.
I don't have any group.
Yes.
You told something to do.
Yes, you have to, because if you look inside, let me share, let me try, I need to stop this one first, I guess. So let me share you this.
Hello.
Let me try to share my tabs. Okay, so if you look here, all right, okay, so you will find the no group tab down here. Here. So you have the T1 and T2, and then T3, and then we have no group. Those without a group, just put your name here, okay? And then I will try and see. I will try to assign you to any groups that the appropriate group. Okay. So for those group who have 5 members or less, please maybe you will get a new member. Or for if let's say you only have 2 or 3 people, there's a possibility that your group may be separated to make sure that we have a good number of group. Okay, is that all right, Gori? Yeah. So
Yes,
please
doctor.
put your name. So please put your name under the no group for those of you who have no group. Okay, please make sure you mention the tutorial group. All right. Okay. All right. Any more question? Good. No more. All right, so let's continue our lecture for today. But first, I want you to do some pre-test. So this is not like contribute to your how do you call that, your marks or anything. It's just to see because this is actually part of an active learning analysis that I used to do in the previous 2 sessions, if I'm not mistaken. So so I would like to just continue gathering some information about this. So can I have you to do this pre-test for like quickly 2 minutes? It doesn't have to be right or wrong because you're not supposed to know anything. And then there will be another post test later after we do our tutorial, and then we will see whether if there's some indication of understanding of the topic. Can we do this very quickly for 2 minutes?
Okay.
Yeah. Yes, Hafiz. Why? Oh, for the link, is it? Oh, okay. For yeah. Do you need the link? I think your friend already posted the link there. Okay, 1 more minute. Just quickly answer the question.
Doctor, I'm from tutorial group 4. There is only slot for tutorial 1 to 3.
Yes. I'm so sorry. I forgot about tutorial 4 and 5. So this one is only for my tutorial group. Tutorial group 1, 2, and 3. I'm so sorry. I forgot to mention that. Thank you for telling me this.
Yeah.
Leave the answer. Yeah, you can leave the answer empty if you don't know. Yeah. It's not you're not going to be marked by this. It's just that I just need to trying to gather some data in regards to student understanding based on this topic. Okay. All right. Okay. So let's continue our lecture for today. So basically, in this lecture, in this topic, we're just going to look at several sorting algorithm. And they are bubble sort, counting sort, radix, bucket, and shell. Okay, so I know you are very, very, very familiar with bubble sort because I believe that uh, um, that is the first sorting algorithm that you actually implemented, I believe, when you learn programming 1. Okay, and then counting sort, radix sort, bucket sort, shell sort. So have you heard about this sort before? This sorting type before, class? Have you heard about counting?
No.
Only bubble.
No. Only bubble. And I believe we have looked into insertion sort. Yeah. Okay. So those are the two sorts that you know. Okay, meaning you're familiar with. So today we're going to be looking at counting, radix, bucket, and shell sort. Okay. All right. So just a brief introduction in regards to sorting algorithm. So if you look at the definition of sorting, literally it means like you are trying to arrange the data into a particular format. Okay, and then for sorting algorithm, normally it will contain some set of instruction for you to use in order to sort your data into particular order. Okay, so your input data may be in a form of array or list. Okay, so you will use this as an input data, and then you will somehow run the sorting algorithm to get the output. So it depends on whether you want it, like in a particular order or in a particular format, and so on and so forth. Okay, and for the common sort operation, normally you applied it onto numerical form, okay, or you are trying to do a sorting for like strings and so on, so characters, okay, which we call it as lexicographical order. All right, so alphabetical order and so on and so forth. So we call it as the lexicographical order. All right. So why do you need sorting? So I mean, like, when you talk about sorting, it probably like you might feel that sorting is just something like a pretty straightforward things to do, thing to do, okay. But then it is actually the most fundamental problem when you study the algorithm, okay, because whenever you are trying to develop something, you will somehow like if, like, let's say, especially you are dealing if you are dealing with data, you definitely will have to apply some kind of sorting to make sure that your data is how do you call that, presented properly, okay. So basically, and then sometimes your system may need the application to have the data to be sort in a particular order for it to like, let's say, for example, perform an operation like searching of some kind of data, or as I mentioned just now, you can you normally apply sorting so that you will have your data to be presented in a more readable format. All right, so that's why sorting is kind of like very important, and it is very fundamental, especially when you're trying to learn, when you are learning the algorithm. Okay, all right. So I believe this is something that you never really consider, because when you talk about the performance of a sorting algorithm, we need to like look at the classification of the algorithm in order for us to see which are the most appropriate algorithm that we can apply for our case. Okay, so you know that when our data is not like general, sometimes you have a very specific type of data, the condition of the data. So you have a very condition of data that you want to manipulate. Okay, so therefore you need to identify the classification of the sorting algorithm that you want to apply, so that you can choose the most appropriate sorting algorithm for your case. Okay, so so for the classification of algorithm, okay, so these are some of the properties that, sorry, I need to change the orientation of my iPad. Okay, so there are several classification that you need to consider, okay, for choosing a sorting algorithm. Okay, so you need to know whether the sorting algorithm is sorting in place or not in place. Okay, whether the sorting is stable or not stable, adaptive or non-adaptive sorting, as well as online or offline sorting. Okay, and then you also need to know in regards to the input and output that you want to have, whether it is an increasing order or non-decreasing order, or decreasing order versus non-increasing order. Okay, so there are different properties between these four sequence. Okay, all right. So let's look at the first characteristic. Okay, first classification of an algorithm that you may consider. Okay, for a sorting algorithm, which is in place versus not in place sorting. Okay, so what does it mean by in place? So for example, like some sorting algorithm may need some additional space for doing comparison or temporary storage of data. Okay, so for those algorithms that require that additional storage, like creating a new array for you to do some for temporary holding the element, it is not an in place sorting. Okay, so it's not an in place sorting. So whatever algorithm that will have that, where you will have to create an additional, like maybe a variable or an array, it is not an in-place sorting. Okay, so for example, not in-place sorting algorithm is the merge sort. Again, I believe you have not looked into merge sort before. So if you have time later, maybe you can look at some videos about the merge sort. But the concept of merge sort is divide and conquer, is applying the divide and conquer, whereby in order for merge sort to sort the array, they have to break the array into two. So it will keep dividing, and then at the bottom it will start comparing, and it will start to merge it back into the sorted array. So therefore, if you look at the implementation of merge sort will have to create an additional array, whereby whenever they break the array into two, they need an additional array to keep the value in. Okay, so therefore merge sort is not an in-place sorting algorithm. So otherwise, if like let's say that sorting algorithm does not require any storing, okay, so in a sense you have the array, and then you just swap the element inside there. You don't have to create another storage. That is called the in-place sorting. So one example is that is the insertion sort. Okay, so if you remember when we do the insertion sort during our tutorial, you will see that all it does is it is just comparing and rearranging the elements back within the array itself. So that insertion sort is an in-place type of sorting, right? Okay. So for the next characteristic that we want to consider when we look at sorting algorithm is whether it is stable or not stable sorting. Okay, so so for a stable sorting algorithm, you can say that it preserves the sequence of input even though after the sort has been performed. Okay, so like let's say for example we have here this array. So this is I think I better put, this is the input array, and then this is the output, which is sorted. Okay, so a stable one. So let's say for example in your input array there's a duplication. Okay, in this case our duplication is these two numbers. All right, so the sequence that these two numbers arrive is being preserved in the output. Okay, so if I like let's say I put this is 3 1 3 2, inside the output the sequence of that element would be 3 1 and 3 2 as well. So it doesn't change the sequence of when it is when the element arrived. Okay, or the sequence of the original array. So for a not stable sorting, okay, so if you look here, if let's say we have this input array, again same thing, we have the 3 1 here and the 3 2 here. If it is not stable, the output, the sequence will be is not going to be preserved. So you'll find that this 3 2 is going to come first, and the other one will come. So the 3 1 will become second. So basically the sequence will be jumbled up. Okay, so normally this thing happen when the algorithm, the sorting algorithm that you use, is comparing with element that is not adjacent. So if like let's say your 3 is here, and then you have some values in between. So maybe this is 3 1, this is 3 2, and then you're comparing with maybe 1, let's say for example. So basically so if like let's say you are so basically there's a possibility that when you compare 3 with 1, there's a possibility that these change places. So 1 could be here, 3, 2 could be here, and 3, 1 could be here. So that is one of the that is one of the characteristic of sorting algorithm that may result in a not stable sorting algorithm, okay, which will result in the sequence of the original array not being preserved, okay. All right. So in this case, stability matters. Okay, you need to make sure that the sorting algorithm that you choose is stable. If, like, let's say, the sequence, you need to make sure that the sequence of original input is preserved. Okay, so let's say, for example, if you have tuples, you want to make sure that they are they are having the same sequence as the original input. Okay, or like, let's say, for example, like when you have an Excel sheet, you will have the names and then maybe age, let's say, for example. So maybe first you sort the name and then you want to sort the age. So if you do not use a stable sorting algorithm, when after first when you sort the name, of course it will go into it will sort in alphabetical order, right? So if you then sort the age, let's say, for example, from the younger to oldest, let's say, for example, if let's say you do not use the stable sorting algorithm, in the after you sort the second time, you sort the age, which is the second sorting, it will jumbled up. It will not keep the alphabetical order anymore. So like, let's say, for example, if you have several 5-year-olds, let's say, for example, so the name may not be in an alphabetical order. So that is one example of why you need to use a stable sorting algorithm if you want to preserve that first sorting. Okay, the sequence of the previous input. Okay, all right, so far so good. Any question? Okay,
Okay.
all right. Okay, so we have looked at online, offline, sorry, in place and not in place, as well as this stable and not stable sorting. So the next one, we are going to see adaptive and non-adaptive sorting. Okay, so for an adaptive sorting algorithm, you can say that the algorithm is adaptive is if, like, let's say, the algorithm are able to take advantage of any sorted input. Okay, so during runtime, um, you know, if, like, let's say, example, like insertion sort, if you remember how insertion sort doing the sorting is that there will be one part of the array which is sorted and one part of the array that is not sorted. So in a sense, the algorithm is called adaptive, is that during runtime, it instead of running order of n squared, it will keep improving, meaning in a sense it will, instead of running uh, through the whole array again, it has the information and it can omit those part that has been sorted. So that is what you mean by adaptive sorting. Okay, so normally you can actually change any sorting algorithm into adaptive, but in a sense you will have to do some housekeeping. Okay, just you need to provide some kind of additional information to the algorithm so that you can change the algorithm into adaptive. Okay, so one of the example is the straight insertion sort. All right, is that right? Okay, so that is what you mean by adaptive. Okay, online versus offline. Okay, so for this classification, you can say that a sorting algorithm is online. It is when that sorting algorithm does not require the whole set of input element to be available when the algorithm start running. So in a sense, you can always add one element in the end, and the sorting will still be able to do the sorting for you. Okay, so if your algorithm allows you to add a new element during runtime, we call it as an online sorting algorithm. Okay, so on the other hand, if let's say you need to make sure that all the input needs to be available before you start doing the sorting, that is what you call an offline sorting algorithm. All right. So for example, an online algorithm is the insertion sort. So you know that since you know already insertion sort, whatever it is, you will have so maybe this one is sorted, and we have this unsorted. So in case like let's say for example we add one more, we are still going to be able to put this inside the sorted array, in the sorted part of the array. Okay, so therefore insertion sort is an example, is a good example of an online algorithm. And for an offline algorithm, we have the selection sort. So I think we are going to be looking at selection sort on this statistic topic. But just to explain to you how the selection sort occurs, is that if like let's say very briefly, is that if like let's say you have an array, okay, it will have 2 pointers. Okay, it will have 2 pointer. One is to keep what is the current minimum value in the array, and what is the current item. Okay, so what it does is that, so like let's say for example, I just put like 3, 4, 1, 5, I don't know, 7, 2. Okay, so let's say I have this array. I have 2 pointers, 1 and 2. So one for current minimum. The second one is for the current item. So selection sort is that it will keep track. So this pointer. So maybe the current minimum is longer. It's easy for you to distinguish. Okay, so minimum would be longer arrow. So when you start the algorithm, of course 3 would be minimum, and then the current item arrow will move to look at the next element. This is not minimum, so it will move to the next element. And they found out that 1 is smaller than 3, and now the minimum is here. And then it will continue looking at the next item, looking at the next item, looking at the next item. All right. And then this one, it will change with the first one. So now 3 is here and 1 is going to be here. So basically that is how you do the selection sort. Okay. So in this case, you notice that whenever you cannot add anything new inside that, else it will change how do you call that? When you look for the minimum, it is going to disturb that process. Okay, and then you're not going to get a proper sorted array in the end. Okay, so is bubble sort offline or online? Class? Your friend was asking bubble sort. You know what is bubble sort, right? It's an offline, right? Because you need to compare. So in a sense, you need to have the full array because it's like bubbling up or bubbling down the element. So if like let's say you're bubbling down the element, so if like let's say you have a new element that is lesser than whatever that you have sorted, you might not get the proper sorted element in the end. Okay.
Oh, wait, doctor, I understand
Yes.
offline means you need to have all the data, essentially all the relevant comparison unit stuff. But what does it mean when online, when it doesn't have to have all of the units before? So what does it mean by that actually?
Because okay, what does it mean is that during runtime you can still add element and it can still sort for you. So like, let's say for example you apply the insertion sort, and then let's say for example during your sort you add more elements inside there. All you have to do is just continue the algorithm. You do not have to rerun the algorithm. So in a sense, it can adapt to new elements being added inside the array. So normally you will add the new element at the end of the array. So it will not how do you call that affect whatever that has been sorted previously. So that is what you mean by adaptive. Sorry, by online. Sorry, online. Yeah, is that all right?
Okay.
Okay. Try to look at how insertion sort doing sort and bubble sort doing the sort. So if like let's say during whether after you have sorted the or somewhere in the middle, whether you can actually get the correct answer. I believe for the bubble sort you cannot, because somehow uh, if you are using the original one, maybe you can still use it, but normally for the bubble sort you can actually improve it, and you can actually maybe later on we're going to see that example, because we will try and see whether we can actually make the bubble sort perform better. Okay, even though it's the worst case is order of n squared, but you can actually tweak the algorithm so that it will not go up until n squared. So later on we're going to see how we are going to tweak our algorithm a little bit so that we are not going to achieve the worst case running time complexity. Okay, so we're going to look at that later. So yeah, so basically we have looked at online and offline. And now we are going to look at what does it mean by increasing order versus non-decreasing order. Okay. So, all right. So for an increasing order, we can say that, excuse me. So we can say that if let's say we have, so generically we can say that if it is an increasing order, we will have element that is not repeating, and for if let's say we have an element that have a repeating elements, like in this case we have 3 repeating, we call it non-decreasing order. Okay, so you might find that people that like some especially like in the comments, sometimes you are using increasing, sometimes the author is using non-decreasing. So if you look at the formal definition of both of these sequence, okay, so for the increasing order, we can say that let's say for example we have a sequence, an element A of n, and we can say that it is an increasing order if like let's say our A n is always smaller than A n plus 1. Okay, so and for the non-decreasing order, if let's say we have a sequence A of n, we can say that it is a non-decreasing whereby we have A n is smaller or equals to a n plus 1. Sorry, it's supposed to be subscript n plus 1. All right. So these are the two formal definition that explain the difference between increasing and non-decreasing order. Are you okay? I need some lights. Are you okay with this? Yeah.
So
Same goes.
non-decreasing can be not stable. All non-decreasing, all non-increasing are not stable.
What do you mean not stable?
No, not stable sorting. Because
This is not sorting. This is just the characteristic of the element in the array.
okay.
This is not like this is more like a characteristic of the element inside your array. Because okay, so as I mentioned just now, when you want to try when you're trying to choose the algorithm that you want to use, the things that you need to consider as well are the condition of your input array. Okay, so your input array may be like I believe that it could be like random, sorted, unsorted, nearly sorted, and increasing order and non-decreasing order is also one of the properties that you can consider with your input array. Is that all right? So this is not a sorting characteristic. This is more like for considering how are the condition of the array, the input array that you're going to have. Okay, because some algorithm, as I mentioned, you need to choose whether you need to use a stable algorithm. If let's say you have a non-decreasing, let's say you have a non-decreasing order. Let's say, for example, okay, whether whether it is important for you to choose a stable algorithm or not. So this is the thing that you need to determine during choosing of the algorithm. Okay, so if let's say you only have an increasing order, then it's fine. Maybe having a non-stable sorting algorithm may not be a problem at all. Okay, but if let's say you have a non-decreasing order, you're trying to achieve a non-decreasing order, or your input is non-decreasing order. Okay, somehow you need to choose something that is stable, especially if the sequence is very important. Okay, so that is one thing that you can use by determining whether the input or the output array is increasing order or non-decreasing order. Is that all right? Is that all right?
Yeah.
Okay. So for decreasing order and non-increasing order is the other way around. Okay. So if let's say we have a n, and we can say that it is so sorry, I think there's a typo. This one is decreasing, right? This is obviously a copy and paste. Okay, and non-increasing. Okay, whereby we can say that if let's say we have our n, a n is always bigger than a n plus 1. Same goes for the non-increasing, which is if let's say we have a sequence of a, and we can say our a n could be bigger or smaller, than a n plus 1. Okay, so that is the definition for decreasing and non-increasing order. Again, we have this duplication inside our element. All right. So as I mentioned, in order for you to, like since now you know the classification, like the type of input that you might have, you need to know how to choose the right sorting algorithm for you to use. Okay, so basically what you need to look at is that what are the size of input, okay, and then whether they are nearly sorted, random, reverse, duplicate, okay, and then you need to consider what is the best worst case. Okay, of course, like you will know what is the worst case running time complexity for the algorithm. But let's say, for example, I did mention about the bubble sort. So you can still tweak it for it to not really achieve the worst case. It probably so in a sense it will not get to the 2 to the power n to n squared running time complexity. So basically we can actually try to find what is the best worst case situation that you might get by applying that algorithm. Okay, same goes for what are the good average case. Okay, and what are the range of the input. Okay, what are the universe of the input, because the type of input, the range of input will play a big part in choosing the type of algorithm that you want to apply, especially later on when we try to look into the linear sorting algorithm. There are still some limitation. Okay, so later you will see that obviously one of them, some of the algorithm, if like let's say you have the range is too big, even though that the running time complexity is approaching linear function, you will have to compromise in terms of the storage and so on and so forth. So these are the things that you need to consider when choosing which sorting algorithm to use. Okay. All right. Are you okay so far? So up until now, what we do is that we looked at what are the classification of and that can be of an of a sorting algorithm. Okay. So do you have any question up until this point, class?
Not yet.
Not yet. Okay. All right. Okay. So do you need like a break for a while before we go into the no? So continue.
Yes,
Or
I think
you mean
a
you
break.
have no? You need a break. Okay. So let's take a break for 5 minutes. And then we can continue back at 4. Is that all right? Yeah.
Thanks,
So let's
Oscar.
take a quick break.
Okay.
Yeah. Right. Please make sure you sign your please make sure you sign your attendance. All right. So how was this semester so far? Okay. This is already week 3. It's very fast. Okay. Can we continue?
Yes, Doctor.
Okay. All right. So up until this point, we have looked at some of the characteristic of a sorting algorithm. Okay, so hopefully with like since you know those classification already, when we go through each of the sorting algorithm, try to identify whether the sorting algorithm is classified under which characteristic. Okay, either they are offline or online, adaptive or non-adaptive. We have what else? Whether in place or not in place. Okay, and then what else? One more. Offline adaptive, stable or not stable. Okay, so and then try to identify as well whether that algorithm is appropriate if you have a non-decreasing sequence or non-increasing sequence as well. Okay. So as we go through each of the algorithm, try to classify the sorting algorithm into with the appropriate classification. Okay. So let's try and look at the first one, which is bubble sort. Okay, so the reason why I start with bubble sort because we want to try to compare, like how far the performance, the bubble sort that we normally use, okay, to sort our array with the one that we're going to see later, and how will it perform if, like, let's say, it is being applied at a big input size and so on and so forth. Okay, so it is not to say that bubble sort is not good. Bubble sort is still very much perform well for maybe I would say a small size input. Um, but then we're going to see how what are the running time complexity and how we can actually improve this algorithm. Okay, so I believe I do not have to like explain how we do the bubble sort, right? So basically, we'll have the pass. Okay, so if you look at the algorithm here, we will have the first for loop, which is the which will talk about how many pass that you have to do, and then this will be where you will do the comparison. Okay, where you will be bubbling up the elements or bubbling down the elements. Okay, so if let's say for example we have this unsorted array, what we do is that for the first pass we will, so basically we consider this as the first pass, we compare, and then smaller we swap, compare, not smaller, we compare the next one smaller and we swap, and we compare, and then this one is still fine, so we do not swap. Okay, so this is the first pass basically. Okay, so for the second pass we do the same thing again from the beginning. We compare, and then if it is smaller, then we swap. Not smaller, we just continue on, and uh, um, how do you call that, and until we get the sorted list. So in this case, how many pass will we do? So normally what we do is that we will do n pass, right? So if, like, let's say we have n element, we will do n pass, n pass. Okay, so if you look at this algorithm, you probably notice something different. Okay, what is the different in this case? Did you notice what is the different?
Pseudocode?
Yeah, the pseudocode. So like normally what you do is that if, like, let's say you have 5 elements, 1, 2, 3, 4, 5, what you do is that your for I is equals 1, and then your for loop will run up until n times, right? Since you want to make sure that it runs 5 times. You did it 5 times. But there is something different with this algorithm, which actually, okay, so if, like, let's say we have the original bubble sort, we know that the running time complexity, the worst case we can achieve is order of n squared, right? So if, like, let's say you have n is equals to 5, let's say n is equals to 5, 5 times 5 is 235.
25.
Yeah. 5 times 5. 5 squared. 5 is 25. Okay, so you will have 25 swapping and comparison occurring in the algorithm. Okay, but for this one, you're not going to get 25. You're going to get, definitely you're going to get less comparison. You're going to do a lesser comparison. Do you know why?
Because of
No, I
minus
think
1.
no, wait.
Oh.
So A length minus, no, this one is the original one, sorry. There's actually, you need to do something to this one so that you do a less comparison. Okay, for this one, So what is the running time complexity for this one? If we look at the first for loop, what is the running time complexity for this one? How many times that it will run? It will run n times, right? For the second, it will run n as well, and then this is 1. So basically, you will get the running time of this bubble sort is n to the power of 2. So if like, let's say our element is 5, so therefore we're going to have 25. If like, let's say our n is 5, our comparison that happens here, this will happen 25 times. Okay, so is there any way that you can actually improve this? You know, like perhaps like have less than 25 comparison. How would you know, like improve this bubble sort? Because if you look here, what you do is that you can actually reduce the number of comparison. I don't know whether we still have time for this, but maybe I'll leave it up to you, okay, to see how. Okay, so the question, the thing that you may take home today. So think about how you can improve the bubble sort, the bubble sort, worst case, should I say worst case? Worst case, a running time complexity. I should not say to improve the worst case. It's not really improving the worst case, but not getting to that worst case. Okay, so try to think about that. How to improve the bubble sort to not, I think, not arrive, not achieve. Not achieve. Maybe I would say the word not achieve. Worst case running time complexity. Okay, so try to think how you can improve this algorithm so that if let's say you have n element, 5 elements, how you can reduce the comparison to have less than 25. Okay, so I'll leave it up to you as something that maybe you can look later. All right, so this is the bubble sort. So we know the running time complexity of bubble sort is order of n squared. Okay, all right. So let's look at counting sort. Okay, so this counting sort, I really like this counting sort. The first time when I look into this counting sort, I think it was like brilliant the way that it does. It's so simple and yet it works. Okay, so counting sort is an algorithm that sort element. So normally for counting sort, you apply it on numeric keys. Okay, so you apply it on numbers between a specific range. Okay, so the thing is with this sorting is that it does not do any comparison. Okay, so so for this algorithm, normally this counting sort is being used by other sorting algorithm because because it is fast. Okay, because it is the random complexity for this counting sort is almost linear running time complexity. Okay, so let's look at the algorithm first. Okay, so or maybe we will come back to the algorithm. Maybe we'll just try to do the counting sort example so that you know how it works. Okay, so maybe I will add one page after. Okay, so like let's say we are trying to sort 4, 1, 3, 4, 3. Okay, so we have 4, 1, 3, 4, 3. Okay, so we'll just use this one. So we have this as our input array. So in this case, the array we use 1, 2, 3, 4, 5. Okay. So for counting sort, it uses an additional array for it to do some process in order for the counting sort to sort the number inside the input array. Okay. So for the first one, for the counting sort, it needs to create another array. So let's call the second the second array as C. Okay. So this C array is used to count how many number so like let's say for example inside the array, how many ones, how many twos, how many threes. So it's trying to count how many of the same element is within the array. Okay, so first, in order for us to create this C array, okay, the counting array, we need to check what is the range of our input. Okay, so in this case, what is the range of our input? What is the minimum and what is the maximum number of our array?
1 to 4.
So we have 1 to 4. So therefore, we are going to create a 1, 2, 4 array. Okay, so we have 1, 2, 3, 4. Okay, so that would be the counting array that you need in the counting sort. All right. So the next step that we need to use, that we need to do, is that we need to count the element inside the array. Okay, so like, let's say for example, we run through this. Okay, so let's say we look here. Okay, so the first element is 4. So we count inside this 4 array as 1. And then we look at the second one. We look at 1 and we count this as 1. We look into 3 and then we count 3 as 1. And we look at 4. We count 4. So this one is the second occurrence of 4 inside the array. So therefore we increase this into 2. Or maybe I should not delete that. So 1. So now it becomes 2 because it is the second occurrence in the array. And then we look at array 5, 3, which is also the second occurrence of 3. So this one we increase by 1. This one becomes 2. Okay. Is that alright so far? You are counting the element. How many elements there are inside the array. Okay. So for the third step, okay, what we want to do is that we are going to calculate the running value inside the array. Okay, so what we're going to do, so maybe I will just draw back the C array here. So we have 1, 2, 3, 4. We have 1. So this is 2, 2. So this one we put 0. Okay, so it's supposed to be 0. Okay, so we are going to calculate what is the running sum inside the array. How we're going to do that is that we're going to add the previous value with the current value. Okay, so let's say for example, this one, because since this is the first element, this is 1. So the second element is 1 plus 0. So this one becomes 1. Okay, for this element, 1 plus 2, this one becomes 3. So for the last element, this is 2. 2 plus 3, this one becomes 5. Are you following so far? We are calculating the running sum. The running sum for the counting array. So this one, maybe I will draw it more nicely again. So this will become 1, 1, 3, 5. Okay? Are you okay so far? Yeah?
Okay.
All right. So now we are going to sort our array using this array. Okay. So since we have 5 elements, so we're going to draw back our array. Okay. This is going to be our resulting array. So 1, 2, 3, 4, 5. So it's 1, 2, 3, 4, 5. So how are we going to sort this back? Is that we're going to look back at the original array. Okay, so let's look at 4. So 4, so this one is 1, 2, 3, 4. So we want to look at 4. So 4, we are going to look into this array of index 4, and the value of index 4 is 5. So we put 4 inside index 5, and we reduce this by 1. So now this one becomes 4. All right. And then we look at the second element inside here, which is 1. We're going to look at the counting array of index 1, and the value of index 1 is 1. So we put 1 inside here. And this one, we minus 1. This one becomes 0. We look at the third element, which is 3. We look at array index 3, and the element inside index 3 is 3. So we put 3 inside index 3, and this one we minus 1, this one becomes 2. Next, number 4, we look back again at index 4. Okay, inside the value of index 4 is 4. So we put 4 inside index 4. This one we minus 1, this one becomes 3. We look at the last one, which is 3. We look at index 4, and what is the value inside index 3, which is 2. So we put 3 inside index 2. This one, 2 minus 1 becomes 1. And therefore, we get our sorted array. We got our sorted element. The array is sorted. Are you good so far?
Yes, but
Okay. Yeah. So did you notice we do not do any sorting? All we have to do is just count, calculate the running sum, and then we just place it according to whatever value that we already calculated. Okay. Yeah. Maybe you can try. Could you explain the last part?
Doctor, so basically after calculating the number of each digit or unit element, go through you then go through all the elements, so all the counted elements, and then just put according to the number that they had, the number that they have as the index, and then just slice one and then continue like that. So,
You miss one step, which is calculating the running sum. So you need to calculate the running sum first. Okay, so what happened here just now is that here is where I do the counting. I count the element, right? And the resulting array is this 1, 0, 2, 2, right? Correct or not?
okay.
And then after that, we are going to do our running sum. So how do we calculate the running sum? Is that we add the sum of the previous index. Okay, so let's say for example, for the first one, this one, the value is 1 because we have no previous index. For this one, we add 0 with 1, therefore we get 1. So for the next one, we add 2 with 1. That's why we got 3. Maybe I'll try to do this again. Okay, so so basically after we count our 1, 2, 3, 4. So after we count our element, this is what we get, right? So we're going to count what is the running sum. So the running sum is we add whatever that is before, and then we add the previous element, and then we get the running sum. So for example, this one, the running sum is you plus it with the previous one. So there's no previous element. So this one is 1. So next we add this one with this one. We plus. So this one becomes 1. So then we add this one with this one. So 1 plus 2, this one becomes 3.
3.
And then this one with this one, we plus, it becomes,
Five.
one becomes 5. Okay? Alright. So basically, so then this is our running sum. So I think pardon this, I try to make it like nicer. So 1, 1, 2, 1, 1, 3, right? Is it this one? 1, 1, 3, 5. Okay. So 1, 1, 3, 5. Now we are going to put back. So we are going to put back. We are going to do the sorting based on this running sum. Running sum array. Okay, and how you do it is that you look at the input element. Okay, input array. Look at the first element. The first element is 4. Okay, so 4, you look into the index 4. And then with the index 4, you look at the element, you look at the value inside the index. And then you look at the index here. And then you put the 4 inside here. Do you see? And then this one minus 1. So this one becomes 4. That is a step. Is it okay? So the next one, let's try and look at the next one. Again, now we look at this element. Okay, 1. We look at 1. 1, we look at index 1. And then after that, we look at the value inside the index, which is 1. We are going to put 1 inside. And then this index, since it's 1, we look at index 1. And then we're going to put 1 inside the array. So this one becomes 1 minus 1. This one becomes 0. Let's look at the next one, which is 3. Right? 3. We look at index 3. And then we look at the element inside index 3, which is 3. And then we look at the index of the output array, 3. Okay. And we put in our 3 inside index 3. And this one minus 1. So this one becomes 2. Are you good so far?
Yes,
So
yes.
we look at the next one. The next one is
Doctor,
4.
could you repeat the 2? How did it become 2 after the minus?
How did it become 2? Because I already put the 3 inside here. So whenever you extract whenever you have placed the element inside the output array, you will have to minus 1 from the running sum.
Oh, okay. Thank you.
Yeah. Okay, so we look at the next element, which is 4. Look at index 4 again and see what is the value inside index 4, which is 4. Since this one we already minus 1, so now becomes 4. Now look at index 4 and we're going to put back the element 4 inside index 4. Same goes for the last one, which is this one, 3. We look at index 3. We look at what is the value inside index 3, which is now it is 2. We look at index 2 and we put our 3 inside index 2. Is that okay? Come on. The last part. Is that okay? Yeah? Alright. Okay, so that is the counting sort. Alright. So, I wonder whether we can complete this one or not. Okay, so the radical complexity for the counting sort. So let's look at the algorithm here. Okay, so since we have this for loop, okay, so because you notice that the first for loop is going to be where you're going to count the element. The second one is where you will do the running sum. Okay. All right. So um A to length AJ plus 1. Okay. CI now normal of equals to 1. Okay, so basically we have four for loops here. All right. So what is the time complexity for the first for loop? How many times does this one happen? It is k, right? 0 up to k, so it will happen k time. And then for this one, it will happen n time, right? For the third for loop, this one will happen k time. And then the fourth for loop, it will happen n times as well. So what is the running time complexity for this one? For this counting sort? It is, this is an iterative calculation. NK, why it become NK? Because this one is not nested for loop. This is not a nested for loop. So this is equals to n plus k plus n plus k. Right? To n plus k. And therefore, we can say that the running time would be n plus k. Right? We omit the constant. So the running time is n plus k. So this is almost linear running time complexity, right? So imagine if you have like a big element to sort, then the running time complexity is very good because it how it grows is that it grows with the number of elements. All right, but as you can see, one of the drawback of this is that you have to make sure that your range is not big. Okay. All right. So this is similar to what we have done. Okay. So you can look through it again. Okay. All right. So the running complexity is n plus k. All right. So the next one, the next type of sort that we're going to see is we're going to look at bucket sort. Okay. So as the name implies, how we're going to apply this bucket sort is that we're going to create a container, okay, for keeping our elements that we want to sort. Okay. So for this bucket sort, okay, so let's okay, so maybe before we go into bucket sort, we need to understand something first. In order for bucket sort to perform properly, we need to make some assumption. Okay, so one is that the assumption is that there are uniform distribution between the bucket. Okay, so in a sense, you have to make sure that input numbers are uniformly distributed between the between all buckets. Okay, so let's say for example, if let's say you create an array of buckets, so each of these array will have the same almost the same number of elements. So like, let's say you have 1, 2, 3. Maybe I'll make it smaller so that it'll be easier. So let's say you have 9 elements, and basically what you wanted to achieve is that at least most of the bucket is being filled, and it has like 3 elements each. Okay, so that is what you're trying to achieve, which is uniformly distributed. So maybe you probably not going to get equal distribution, but at least the distribution is not too how do you call that, too unbalanced. Okay, so this is what we're trying to achieve, which is uniform distribution. All right. Okay, so basically the idea is to divide the bucket into equal size sub-interval or the bucket. All right, and then distribute the numbers into the bucket. After that, in a sense, you are to expect each of the bucket to contain at least a few numbers. And then within the bucket, you need to sort each of the element in each of the bucket. Okay, so normally you will use the insertion sort because it is a stable sort. So normally, if you want to use the another sort as a subroutine, try to find a sort that is stable. Okay, so insertion sort is stable. So so you use the insertion sort and then go to the bucket in order, and then you list out the elements again. Okay, so let's say for example, if I have this array 28, 24, 4, 48, 8, 36, 32, 43. Okay, so I know that my range of elements is from 0 to so in a sense I can see that how I can create a bucket is I can create a bucket of 0 to 9, 10 to 19, 20 to 29, 30 to 39, 40 to 49. Okay, so basically I can see that this would be the most appropriate, but not appropriate, but one of the way that I can create my bucket. Okay, so and then I go through my array. So 28, I put it inside this bucket because this bucket will hold the range of number between 20 to 29. So I put 28 inside there. 24, I look, so it is still within this bucket, so I put 24 here. 4, it is within this bucket, I will put 4 here. 48, this is within this bucket, so I put 48 here. 8 is within this bucket, I put 8 here. 36, it is within this bucket, so I put 36 here. 22 is within this bucket, I put 22 here. And 43 is within this bucket, I put 43 here. Okay, so it's pretty straightforward. It's just that you create a bucket with the appropriate range, and then after that, you try to put in all the elements inside each of the bucket, and then after that you sort the data. Okay, so you sort this bucket, you sort this bucket, you sort this bucket, you sort this bucket, and you will get this. Okay, you have 4, 8 sorted, 32, 24, 28 sorted, 36, 43, 48 sorted. Okay, third step is for you to extract back all the data in sequence. Okay, remember you have to do it in sequence. So you extract 4, 8, 22, 24, 28, 36, 43, 48. Okay, and you will get a sorted array. Okay, so is it when we use any kind of sort to you can use any kind of sorting to sort the data inside the bucket. Yes. So since this one is not like how do you call that? You can use counting sort. You can use insertion sort. But again, normally if you're using another sort as the subroutine of another sort, you need to find, normally what they do is they try to find a stable sort, and something that have the best worst case. So I can still use counting sort, but yet there is a lot of drawbacks. You know, like if you try to how do you call that? Imagine if, like, let's say we want to use counting sort, then you need to provide an extra space for the additional auxiliary array for the counting and so on and so forth. So it looks like at the moment, since we can anticipate that it's not going to be a big number inside each of the bucket, so insertion sort is more than enough to do the sorting within the bucket. Okay. So the only thing is that normally we will use a stable sorting algorithm as the subroutine of the sorting. Okay. All right. You may get a different size bucket and so on and so forth, but whatever it is, we need what we always try to achieve the uniformly distributed. So if you see my bucket, I have like almost uniformly distributed elements within each bucket. Okay, and almost all of the bucket contains element. Okay, so this is another example of a bucket sort. All right, so you can let's say, for example, you have this element. Okay, and then you can also do it if, like, let's say you have point form as well. All right. So what is the running time complexity of a bucket sort? Okay, so if you look here, for the first for loop, what is the number of the execution happen in this first for loop? It would be n.
And
For the second one is also n. The third one is also n. Okay, and let's say we do something here which is order of n squared, right? Insertion sort. But then since we know that it is uniformly distributed, and definitely we are not going to achieve the n squared, and because like even though the worst running time the running time complexity of insertion sort is order of n squared, but we know it will probably be 1/3 or 1/4 of the running time complexity. So let's say, for example, you have 5 elements, maybe you know like if, like, let's say you have to do how, like the swapping, like 25 swapping. Maybe when you use it inside the bucket sort, you're not going to do 25 swapping, you're not going to be getting the n squared. You're probably going to do like maybe 1/4 or 1/3 of the total sorting. So therefore, this one is almost towards constant. Okay. So therefore, n plus n plus n. Therefore, we get order of n. All right. I think we're going to be revisiting the uniformly distributed when we do the hashing. So it has to do with the load alpha. So why it is moving towards constant, we're going to see this load alpha later on in, I believe we're going to do it in hash algorithm. Okay. All right. So that is the bucket sort. All right. The time complexity is order of n. Okay. So the next one is shell sort. Shell sort. Okay. So it's a little bit of tongue twister. So this is a generalization of an insertion sort. Okay. So it is like doing an insertion sort but with a twist. Okay. So normally how we do an insertion sort is we look at the next element. We keep looking at the next element and so on and so forth. But for shell sort, how it tweaks that element is that it introduces gaps. Okay, so these gaps will reduce the running time complexity to be almost towards the worst case running time still can get into order of n squared, because it is an insertion sort at the base, but then you can actually achieve better because of the introduction of the gap. Okay, so let's look at the example straight away. Okay, so let's say, for example, we have 8 elements to sort. So we have eight elements to sort. Okay, and we are going to use this shell increment will be the floor of n over 2. So basically, how we determine the gap is that we're going to use n over 2. So for step 1, we are going to use we are going to use so that, let's say for example our element is 8, and we're going to divide it by 2. Okay, so it will be 8 over 2 floor, okay, which is 4. Okay, since we get 4 would be the gap. I like to, normally this is how I make sure that I can I am comparing, doing the insertion sort within the same gap. Okay, so how I did it is that if, like, let's say our gap is 4, put name it as this one. So we put 1, 2, 3, 4, 1, 2, 3, 4. And what are we going to do here is that we're going to do insertion sort only with the same number of index of elements. Okay, this one. So basically we're going to do insertion sort between these two. We're going to do insertion sort between these two. We're going to be doing insertion sort between these two and insertion sort between these two. Okay, so in this case we do comparison between this one. There's no change. So we just transfer it back into its original position. The next one, we compare this 32 with 33. Again, no change. So we're going to just transfer it straight away into the same position. Same, we're going to do insertion sort on the third one, which is 12 and 16. It's still the same. We're just going to transfer it straight away into this one, right? And the final one, we do insertion sort. So basically we found out that this need to be swapped. So we swap, and now 2 is here, 5 is here. And therefore our first step is done. We need to do this thing again with a smaller gap. Okay. So in step 2, since our current gap is 4, we're going to apply the n over 2. So now we're going to apply the floor of 4 over 2, which we have 2. So now our gap is 2, right? So our gap is 2. So 1, 2, 1, 2, 1, 2, 1, 2, right? So now what we're going to do is we're going to do insertion sort with all these ones. So all this one. So we're going to do insertion sort with all the elements under 1. And we're going to do insertion sort for the element all under 2. Okay. So in this case, let's do the first one. So this one with this one. So somehow this one will swap. So this one become 12. So this one becomes 12. And then you compare. So this one is 18. So now you compare. So you compare 38. So 38 is here. Okay. And then the next one is you compare 16. So you know that 16 has to be between 12 and 18. So now this one becomes 16. This one becomes 18. This one becomes 38. Okay. We are doing insertion sort, but only for this one, this one, this one, and this one. Therefore, we get 12. We get 16. We get 18. And we get 38. Same goes for this element. We're going to do insertion sort, which is so we compare this one. We compare this one with this one. So this one becomes 2. This one becomes 32. 33 is still there. And then we compare with 5. So we know that 5 should comes between 2 and 32. So this one becomes 5. This one becomes 32. This one becomes 33. And therefore, we transfer it down. 32 and 33. Step 2 is done. Okay. And we are going to continue again to the step 3, whereby we take the previous gap, which is 2 over 2 floor, and we're going to get 1. And therefore now we can say that this is all 1. And what we're going to do is just do the normal insertion sort. So we just do a normal insertion sort, and finally we are going to do we are going to get the sorted array in the end. Okay? Are you okay so far for the shell sort example?
Doctor, I have a question.
Yes.
So in the example that Doctor given, the sample size is 8, right? So it's an odd number. So what if even number? So what if the sample size is odd number, like say like 7 or 9? So how is that going to be sorted?
You take the floor. Take the floor. So 7 over 2. What is the floor of 7 over 2?
3.
7 over 2 is 3. The floor, right? So the gap will be
Yeah.
3. That's why here, how you determine the gap is I take the floor. So because we want to, we are considering as well, if like let's say, we have an odd number of elements inside our array. Still the same thing, you put the number in and only compare the one with the same, within the same gap. Is that alright? Munir? Is that alright?
All right, I can see now.
Okay, so you try and do it, and then maybe you understand better. Okay. All right. So for the shell sort, the running time complexity can vary. Okay. So as I mentioned, it can go up until order of n squared because it is essentially an insertion sort, but you introduce some kind of gap. So the running time complexity will depend on how you get the gap sequence. Okay. So if you look here, there are many ways that you can do the gap. Okay, so the one that we use just now is the shell one. So it can, the worst case running time can go up into n squared. Okay, so so if let's say you use a different way of defining the gaps when you do the sort, so you're probably going to get something better. Okay. Excuse me. Oh my god, now I'm starting to lose my voice. Okay, so you're probably gonna get something better like 3 over 2, right? The power it will be much more faster. Okay, so it depends on how you do the gap, but the original one is n over 2. Okay, all right. So is this the last one, Radix sort? I think it's the last one. Okay, so Radix sort, again, there's no comparison, but then it is using some kind of subroutine sorting within the sort. Okay, so for the Radix sort, it sorts data according to the keys, and then how they do is they group the keys according to the individual digit which share the same significant position and value. Okay. And then using counting sort, okay, or any stable sorting, you sort the element, and then you keep doing it for each of the digit. I think maybe we just straight away look at an example. Maybe not this one. This one is quite big. So let's look at a simpler example. Okay. So like, let's say, for example, we have this array. Okay, so this is the array that we want to sort. So first, we need to determine what is the digit that we have. So in this case, the largest digit we have is the 3 digit, which is 803171. So therefore, our D is equals to 3. Okay. So what we're going to do is first we are going to sort the ones places first. This I don't know, you call it ones, right? Ones, the puluh is what? The tens and the hundreds, right? Yang puluh ratus in bahasa. Last time my maths is in bahasa. So basically how you sort it is you look at the position of the digit. Okay, so we don't really look at the value of the element. We look at the digit specifically. Okay, so how do we do it? Is that we look at the least significant digit. Okay, and then we sort it. We have to make sure that the sequence is not changed. Okay, so basically we look at 1, we look at 6, 6, 1, 3, 4, 6, 7. So we know that we got 171. We got we got 491 here. And in our original number, we don't have 491. I think this one is 491. How come we have 491 inside here? I think this one is a typo. This one is supposed to be 0. Because I don't see any 491 in other array. Okay, so that's a typo. Okay, so we have, so basically 1. So 1. Okay, so that is the first one. So we put 17191. And then 2, what is the next smallest one? So 803, right? We put 803 here. And then 4. And then after that, what is the next biggest number? 6, right? So 46, 76, 26, and the last one is 67. Okay, so that is so funny. We get the second output. Okay, after sorting according to the least significant digit. So for the next step, we try to sort according to the second one, this one. Okay, so it starts with 0, so 803, 004, and then the next one to 26, 26, 46, 67, 171, 076, and 91. Okay, so we don't really look at the number as a whole, we just look at the digit. So same goes for the third one. We're going to look at the most significant digit over here. Okay, which is so without changing the sequence, yeah. So 004, 026, 046, 067, 076, and 091, and then 171 and 803, and therefore we sort the array already. So that is the Radix sort. Do you see how the Radix sort is being done? Plus,
Yes, kind of. Yes.
there's nothing complicated. You just look at the number and just make sure that you sort according to the digit and do not change the sequence at all. That's why stable sort, for specifically for Radix sort, you need to make sure that you use a stable sorting algorithm for this one. Okay, and the running time complexity for this one would be, so this one, how many times it occur is, which is D. And then let's say, for example, we are using a counting sort. So what is the running time complexity for counting sort just now? N
N plus K.
K. So therefore the running time complexity for Radix sort would be
D time N plus K.
D times N plus K. Okay, so that would be the running time complexity for Radix sort. All right. Okay. All right. So any questions so far? So today we have looked at several sorting algorithm. So we have looked at other than bubble sort, we have looked at counting sort, we have looked at bucket sort, we have looked at shell sort, and this one, the Radix sort. And this is not the only sorting algorithm that you can find. So you will definitely see a lot of variant of sorting algorithm. In fact, we're going to look into several more in the next lecture. So merge sort, we're going to look at merge sort in divide and conquer. We're going to look at selection sort. We're going to look at heap sort. So all this is used to do sorting, but they have their advantages and disadvantages. Okay. So I have this one website that if you want to see the visualization of this, so let me try and get it out. You can go here. I'm going to post the link here in the chat. Wait, let me try and. Okay, so yeah, okay, so you can go into this website. Okay, and then you can see the how do you call that, the visualization of the algorithm, and in fact it also contain visualization of other algorithm as well. So this is actually a good website. This is actually one of your senior actually texted me that she found this website that maybe it's good for you to actually use in class. Okay, for algorithm, which is actually good. It will show you the visualization of each of the algorithm. So they have the sorting algorithm inside there. So have a look and maybe you will understand more on how it is actually working. All right, as compared to the algorithm as well. Okay, this is for tutorial 1, 2, and 3. So as I mentioned, we are probably going to, like do some group discussion and so on and so forth. So I know that inside the tutorial you have like only one set of array that you need to apply all these algorithm. But for tutorial 1, 2, and 3, please try to take this example and apply the algorithm to sort this array. Okay. For each of the algorithm, as I mentioned, it's good for something and it's bad for something else. So so I think for the time complexity, it's clear cut. So we have discussed this in class. But then I want you to try to discuss what are the best application condition of the algorithm, okay, by taking into consideration, like let's say if you have a nearly sorted order, how will the running time complexity be affected by those, okay? And then maybe for the algorithm, you can just copy back, or if you have if you find a variant of that algorithm, okay, you can also share it during the class. And then, as I mentioned, because since we know what are the classification of sorting algorithm, try to discuss the classification of each of the algorithm as well. Okay, so for tutorial 1, 2, 3, try to get, you can do this in a group. I would totally recommend you do this in a group. Put this like, create a Google Drive, and then be ready to give the links to me, and then during the tutorial, we can have a discussion. Is that okay? Class? For tutorial 4 and 5, you can use the tutorial question that is in the spectrum. Or if, like I said, Dr. Raja is having a different one, then you can use that. Okay. So yeah. So do you have any question? I'm so sorry. I sort of like take extra time. I think because I need we spend like 15 minutes or something else in the beginning.
So
any question?
So what we need to do is the thing in this PDF. Yeah.
In this question, yeah.
Okay.
So Yeah, so just use this as the question and try to discuss this in terms of classification, limitation, advantages, type of the when should you apply this, when you should not apply this algorithm, and so on and so forth. Okay. uh, uh, Trust me, like if you do this correctly, you should get some of the group will get a different answer for some of the algorithm. Share any resources that you found, and then we do again crowd uh, uh, knowledge, crowdfunding for knowledge for certain algorithm. And if you find any interesting facts or interesting algorithm that you came across that is related to what we learned, please do like include that as well. And we'll try to like have a chat during the tutorial and discuss about this. Is that okay, class?
Okay.
All right.
Yes, Doctor.
So in that case, let's end the class for today. Again, sorry for overrunning like almost 3 minutes. Hopefully you are still awake. Yeah. So that's it. So I'll see you during tutorial. Okay. So please, I think if I believe that I need to also like update you with some of the announcement regarding the lab viva, or whether you want to do a synchronous or a face-to-face lecture for the string matching topic. Okay, but I think string matching is not that critical. It's pretty easy concept to take up. Okay, so if you think that you need me to like just like have a session where you want to ask question or anything, you can just let me know. Okay, either text in Telegram or Teams. Okay. All right. In that case, I'll see you on Thursday. Okay. All right.
Thank you, Doctor.
Bye.
Okay.
Bye.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you.
Thank you, Doctor.
Bye.
Thank you.
Thank you, Doctor.
Bye bye.